All right, well, let's get started. So it's my pleasure to welcome Michael Xie, who's here from Stanford. He's doing his PhD advised by Percy Lang and Teng Ma. And Michael works on the secret sauce that makes all the great models work, which is data. So how do we train on data? How do we optimize the mixtures? And why does the training work, including some theoretical analysis of mechanisms like in-context learning and fine-tuning the adapters. So I will stop talking and let Michael give the rest of the talk. Let's welcome him.
Thanks very much. Thank you very much, Jason. And thank you very much for inviting me here. I'd like to talk about some of my work on data distributional approaches for generalizable language models. Okay, so I asked ChatGPT to write code for me for a modern academic personal website. And I also put in some of my personal information. And this is what I got. It's a website that looks arguably better than my actual website. And this is when I realized, gosh, these language models are going to revolutionize the way we do code development. And I think it's revolutionizing not only that, but also the way that we do science, finance, medicine, law, and art. So clearly, there's been an explosion recently in AI progress. The first question I would ask today is, what really drives this progress? I argue that large-scale data drives the progress in language models. So here I've plotted this, the size of data sets used to train popular models today in a log scale over time. And you can see from this plot that the data sets are growing exponentially. And this is both a blessing and a curse. It's given us better capabilities in these models, but it's incurred huge training and data curation costs. To get an idea of these costs, we can take a look at the Google PaLM model, which is one of the last models we have public stats for. It's trained on 700 billion tokens, 780 billion tokens on 6,000 TPUs over 2 months, and it costs about $10 million to train. So this is obviously super, super expensive. The root of the matter is that this is a huge model trained on a huge data set. And so the central question here is, can we improve the data to achieve better capabilities more efficiently? To get an understanding of the gravity of this question, we can take a look at the GPT-4 technical report from OpenAI, which doesn't have any details about the data, but we can take a look at the makeup of their team. And we can see that the data team was the largest in the GPT-4 effort, and it speaks to the relative importance of data in their pipeline. But in the broader community, there's been a relatively less focus on the data side. The dominant paradigm is to keep the data fixed while focusing on the models and the training algorithms. And due to this, we've gotten a bunch of great architectures, optimizers, and objectives, but fewer methods for curating large-scale data. And I argue that in the machine learning pipeline, we need to focus on data curation as an integral step. So while we have an extensive training and modeling toolkit, the data curation side is relatively underexplored and based on ad hoc heuristic methods. So some of the work I'll talk about today is on data curation, and in particular, our contribution is on principled algorithms for large-scale data curation that's been used to train some of the leading language models in practice today. And beyond this, we need to further understand how data affects model capabilities so that we can design better algorithms in the future for data curation. So I worked on 2 broad areas within this understanding aspect. First is on understanding how pre-training affects downstream performance in both language and vision, in contrast to pre-training, mass language modeling, and next token prediction, and how that translates to in-context learning. And as well as pre-training for robust machine learning, the ability of models to generalize beyond its training distribution. And I've worked on settings such as domain adaptation, out-of-distribution generalization, and adversarial robustness with some applications to poverty mapping in remote sensing, which have appeared in the journal Science. And our broad contribution here is in understanding how pre-training can help the model capture the latent structure in the data, and how that leads to more generalizable models that are more robust and accurate. So as an outline for the talk today, there's 3 sections. The first 2 are on 2 major settings in data curation for pre-training data. The first is in optimizing data mixtures for multipurpose pre-training. The second section is in selecting data for a specific target distribution instead of a multipurpose model. And then in the third section, we revisit the multipurpose pre-training setting to understand a key capability of language models called in-context learning, and in particular with the goal of understanding the role of the pre-training data on eliciting in-context learning, and to give a direction for future data curation algorithms. So as an overview of the talk, I first lay down the foundations for a data distributional view of pre-training, which consists of 2 broad steps. The first step is to train on this pre-training distribution, which is a broad data distribution, for example, web crawl, where the model can build a broad and diverse knowledge base. And then the second step is to then adapt the model on an adaptation distribution. It's a narrower distribution that represents a target task that we care about, for example, code completion. And the goal and the central challenge in pre-training really is to be able to generalize from this broad pre-training distribution to this adaptation distribution that we care about. And all of the settings I'll talk about today are going to be situated within this view. So the first setting is in training multi-purpose models like ChatGPT that can do a large number of tasks like question answering, creative writing, and semantic parsing. We can view this multi-purpose pre-training setting as there being many possible adaptation distributions that are unknown during pre-training time. And what we'll do is we'll reweight the pre-training data in such a way that makes sure that the resulting model can do well on all these possible adaptation distributions. And I'll introduce an algorithm called Do-Re-Mi, which uses robust optimization to tune these data mixtures, and it results in a 2.6 times speed up in pre-training large models. The next setting is in training specialized models, which are more performant on a particular domain like code. Some examples are the OpenAI Codex model, which is a specialized version of GPT-3 that's used to run the GitHub Copilot service, and also the Code Llama model, which is a specialized version of the public Llama model. We can view this setting as there being a particular adaptation distribution that we know about beforehand. And in this case, we'll also reweight the pre-training distribution, but we'll do so in a way that focuses on the relevant data for this target adaptation distribution. And I'll introduce an algorithm DSER, which is a large-scale data curation algorithm that leverages importance resampling and improves over both manual curation and heuristic filtering methods. And then finally, I'll revisit the multipurpose pre-training setting to understand this capability of language models called in-context learning, where with just a few examples of a task, the language models can learn, quickly adapt to do that task. So here we have this prompt where we have a couple of examples of an antonym task that we want to do, as well as a test input that we want to make a prediction on. And the pre-trained language model is able to both understand the task and make the prediction in one forward pass. And we can understand this as there being, as the language model's ability to quickly adapt to many adaptation distributions just by conditioning on a few examples sampled from that adaptation distribution. And we'll analyze this, how this can occur. And our understanding is that it originates from the model modeling this latent structure in the pre-training distribution, in particular, this long-range coherence structure in pre-training documents. And in particular, our contribution is in providing a first theory for in-context learning. We can use this understanding to construct a small synthetic data set with the same latent structure, where if we pre-train models on this synthetic data set, we also elicit this in-context learning behavior. Okay, so I'll jump into the first section where we optimize the data mixtures for multipurpose pre-training. So in this setting, we consider that language modeling data typically comes from many data domains, data domains, for example, Wikipedia, books, and web. And let's say you have a fixed budget. The question is, how much of each domain should we train on? This is a tricky question because there's no particular target to focus on. So how do we choose this weighting? Some previous approaches have used manual tuning and intuition, for example, in the popular PILE dataset. They take the natural distribution according to the sizes of each domain, and then they upweight the particular domains that they deem to be higher quality. So for example, Wikipedia and books are deemed high quality because they've gone through some sort of editing process. But this can be suboptimal because it's just based on intuition. Some other approaches have tuned against downstream adaptation tasks using a heuristic search process with pre-training in the inner loop. However, this can overfit to this choice of adaptation tasks used, and it can be quite expensive. You might have to train many sizable models to get a good signal on the downstream tasks. So we instead formalize the problem as robust optimization. So the idea here is that we have this unknown target. Can we choose the mixture so that the model is robust to this unknown target? And in particular, we'll do so in a way that the model does well on all the domains simultaneously. And so the robust optimization approach to this is to optimize an objective, which is the worst case loss over all the domains. The actual optimization problem we solve is derived from the group distributionally robust optimization, or DRO, problem. It's a min-max optimization problem. We're minimizing over the set of model parameters theta, maximizing over a set of domain weights alpha, and the objective is this worst case weighted objective over domain level losses. Yes.
So can you just distinguish between training and test loss?
So here we're in the one epoch training setting. So in our algorithm, we'll use the training examples themselves as the measure here. But I think in general, you do want to measure how each domain is doing on some held out examples.
Thanks.
Yeah. So the domain weights alpha here are going to upweight the higher domain level losses. And in general, the goal is to find a set of domain weights at the equilibrium point of this problem, which balances the losses across domains. Okay, however, there's an issue in the previous objective. So let's say the lowest possible loss values across domains are as follows, where there's a particular domain that's more noisy. It's got a higher optimal loss. Then what happens is that you use the objective to find some domain weights. We'll find some domain weights that skew towards this higher loss domain. And so there's this sort of pessimism in the objective where it will upweight the noisy or high loss domains. So to resolve this, we instead optimize excess loss, which is the loss gap between a model that we're currently training and a pre-trained reference model. So what I've done here is simply replace the loss in the previous slide with a difference between two losses. And so to get an intuition of what this is doing, for example, if the excess loss is small, then on the example X, perhaps we've already learned that example. So L theta of X, the loss of the model we're currently training, is already small, or that example comes from a noisy or not unlearnable distribution. And this would happen when the reference model's loss is large. On the other hand, if the excess loss is large, then there's large room to improve on this example, so we should try to upweight it. For convenience, in the next slide, I'll notate the inner part of the objective as L of theta and alpha. So how do we actually optimize this objective? So in general, we do this alternating optimization loop between the domain weights and the model parameters. We first update the domain weights, alpha t, in such a way that upweights the domains with higher excess loss. And now given these updated domain weights, we can then update the model with the objective L. At the end, we'll return the time average domain weights across the steps of this optimization. And I'll note that we use DRO here to optimize the domain weights instead of training a robust model, which is how it's typically used. So with these ingredients, we can now define our algorithm called domain reweighting with minimax optimization. It consists of 3 steps. You start with an input, which is the reference domain weights. You can just use, for example, the natural distribution that comes from the sizes of each domain. You use these domain weights to train a small reference model. The reference model is used in the calculation of excess loss in the second step, where we train a proxy model using DRO. And as an output, we get a set of optimized domain weights. These optimized domain weights define a new reweighted data set that we can use to train a much larger model in step 3. You'll note that the steps used to optimize domain weights, steps 1 and 2, only train 2 small models here for computational efficiency. And the punchline here is that domain data mixtures can speed up training by 2.6 times on 8 billion parameter models. Yeah.
There's a data set that alpha belongs to, right? So how
so in this experiment, we used the pile dataset, which consists of 22 domains. For example, Wikipedia, books.
Speak louder. So can you go back to the last one? The maximization problem says alpha belongs to delta k.
Yeah. So delta k is just the simplex. Yeah. So just all the possible probability vectors of size k.
It's the force with the point maximum of the loss, right?
Right. Right. For any particular theta, yes, but the equilibrium point isn't so. Yeah. Yes.
Last question, how can you do better than that? Says that you are optimizing to like the same.
Yeah, that's a good question. I think the intuition is that we find a way to dynamically close the gap as quickly as possible. And I think even when we have 0 excess loss, for example, we're still like the goal here is to try to get to the performance of the reference loss in as few steps as possible. And then in whatever extra steps you have, you can then continue to train on that distribution to continue improving. I don't know if that's a good intuition for you. I think what we find is that we'll reach the same performance earlier in training, and so then if you continue to spend more budget, then you'll get to a higher performance. Yes.
Just a simple question. Should we think of, I know you had this on a later slide also, that LREF is from a small model, but should we think of that as basically you're going to fix alpha to be 1 hot and optimize theta just for a single domain?
No. So in this optimization loop, the update rule comes from you can think of it as the exponentiated gradient update rule.
Oh, right.
So you have this just weights over all the different domains, and then you'll see the current losses for the current model, and then use those losses to basically you take the current weight vector, multiply it by x of the excess losses with some temperature,
yep.
And then you renormalize. So it's going to be some running weighted average of
LREF. So you're saying that LREF is just from the previous iteration?
LREF is just you have this pre-trained model that you're evaluating on the batch.
So my question was, is that model a mixture, sorry, is that model a separate model for each domain? So that
No, it's one model. It's one model. So this is a good question. So if you have a lot of data on each domain, I think you can certainly train one model per domain and use a domain-specific model to try to estimate the optimal the entropy of every domain. But there are certain domains here that are kind of small, and actually, if there's not enough data to really train a reasonable model. So and also just for convenience purposes, we just used one model.
So the reference model is like weighted or something.
The reference model is just trained on the natural, yeah, the concatenation, yeah, exactly. Okay, so I'll go into this result further. So we trained models on the pile dataset. It's we used 280 million parameter reference and proxy models and to optimize the domain weights, and then use those domain weights to train a larger 8 billion parameter model, which is 30 times larger than the proxy. So if you look at the downstream performance of these models, the model trained on the Dormy optimized weights in blue achieved the same downstream accuracy in about 2.6 times less training steps. And if you give it the same training budget, it achieves a 6.5% better downstream performance. And I'll note that the baseline here is with respect to the manually tuned weights from the Powell dataset. And doing this domain weight optimization is relatively inexpensive. It only takes about 8% of the compute of training that 8 billion parameter model. So steps 1 and 2 take about 8% of the compute needed for step 3. And then finally, one of the motivations for doing robust optimization was to try to do well in all the domains at the same time. So here I've plotted the losses or estimate of log complexity on each domain on the pile. And we can see that the model trained on optimized domain weights gets better loss on all the domains simultaneously, despite downweighting some domains in order to upweight others. And this is due to some amount of positive transfer across the domains. Perhaps more interestingly, we can actually iterate the process. So we can take the optimized domain weights and feed them back in as new reference domain weights to try to get better optimized domain weights out. And so we tried this on the GLAM data set, which was an internal data set in Google used to train Palm, where we have access to a set of Oracle domain weights that are trained on downstream tasks that we're actually evaluating on with many training runs. And I've plotted the Oracle weights here as horizontal dashed lines. So we started the iterated Dormy process with 280 million parameter proxy and reference models and uniform reference weights. So these are super suboptimal reference weights. After one round of Dormy, these are the weights that you get. And then after you iterate a couple more times, we see that this process converges in the third round. And it converges to something that's similar to the Oracle weights without any access to the downstream tasks themselves. And if you train the 8 billion parameter models on these domain weights, the model gets a similar performance to the Oracle, the model trained on Oracle weights as well. So Dormy has been used in practice in industry at Google and together. It's been implemented on BART and Gemini. It's been used to train some of the strongest public 1 and 3 billion parameter models called shared llama. And it's been incorporated in training libraries like Hugging Face Nanotron and Stanford Levanter. And we're working with a couple of other companies as well to incorporate it in their pipelines. So as a summary, optimizing the data mixtures for multipurpose language models is tricky because there's no particular target to focus on. So our algorithm Dormy instead formulates this as robust optimization to be robust to the unknown target, and therefore optimizes the data mixture using robust optimization. And the result is we get a 2.6 times speed up in training 8 billion parameter models on the pile. Okay, so in that first section, we talked about multipurpose pre-training. In the next section, we'll look at selecting pre-training data for a specific target distribution. And to set this up more, we first assume that we have access to a large raw data set, for example, a web crawl, and as well as a small target data set for the specific target distribution that of interest. And the goal here is to select a subset of the raw data that's relevant to this target distribution. And so the challenge here is that we want to do large-scale selection from possibly billions or trillions of raw examples. A common baseline here is what we call heuristic classification. It comes from the GPT-3 paper. In heuristic classification, you first train a binary classifier, F, to discriminate between the raw and the target data. Here, the F of X is the probability that X comes from the target data. And then in the second step, we can then use the classifier to filter the raw data. So they'll keep in the raw example X if F of X is greater than some noisy threshold. This threshold is noisy just to introduce some diversity, and the noise distribution is a hyperparameter in this method. So pictorially, let's say the target is code. We've applied this classifier on a couple of raw examples here. It'll give a higher score to the ones that look like code, and then we'll tend to keep the ones that are that have a higher score. So, but however, this is a heuristic method. There's no guarantees on the selected distribution that you get out from this process. So to formalize the problem, we first say that we have large N examples sampled from a raw distribution Q, and little N examples sampled from a target distribution P. And the goal is to select K examples from the raw data from a distribution P hat that's similar to the target distribution. And an intuitive approach for doing this is as follows. So let's say we have these 1D probability densities of the target and the raw distributions. What we want to do is upweight the examples that are more likely under the target than the raw distribution, and vice versa. We want to downweight the examples that are less likely under the target than the raw. And there's a classic algorithm which does this. It's called importance resampling. You first compute importance weights. These importance weights, which are the probability ratio between the target and the raw distributions. And these importance weights essentially do what we want. They'll upweight the example if it's more likely under target, P of X, than the raw. And then in the second step, we can use these weights to define a new distribution to resample from, but just by renormalizing these weights. And by doing this, we can sample from a distribution that's similar to the target. However, the issue is that we need to estimate these importance weights, which are intractable to estimate in high dimensions. And we're working in the space of text, which is extremely high dimensional. And in high dimensions, the issue is that we need to estimate importance weights on an exponentially large space. So just to illustrate, I'll go from 1D to 2D, which is slightly higher dimensional. Let's say we want to estimate importance weights for each grid cell in this 2D space. And we have these samples of the raw and target. Here I've just drawn non-discrete data just for illustration. So we can estimate the importance weight by counting the number of raw versus the number of target examples in each cell. However, we don't have enough examples to estimate this well everywhere. And so our algorithm, data selection with importance resampling, or DSER, works around this by working in a reduced feature space. So the idea is to take the raw and target data sets and transform them into a feature space. We learn feature space distributions of the raw and target. We use these feature space distributions to compute feature space importance weights, and then we plug them into the importance resampling algorithm. And so the big question that remains is, what feature space should we use? So in our work, we chose a feature space called that we called hashed n-grams. for simplicity and scalability. So to illustrate what it does, it's so let's say we have this input sequence, Alice went home. We first form a list of n-grams, the unigrams and the bigrams, and then we hash each of these n-grams into a fixed number of buckets. So now we have a sequence of hash tokens. To do importance weight estimation on this feature space, we use bag of words models on these hash tokens. They essentially assume that the tokens are independently generated, and then to learn the parameters of these bag of words models, you can just count the frequencies of the hash tokens. So this is very simple and parallelizable. So algorithmically, this is very easy, but do the hash n-grams actually preserve meaningful information for pre-training? To test this, we came up with this metric called Kullback-Leibler or KL reduction, which is a metric defined on the hash n-gram space itself. We define it as a difference between two Kullback-Leibler or KL divergences, which measure the distance between distributions. The first KL divergence is between the target and the raw distribution, which is typically large. The second KL divergence is between the target and the selected data that comes from the data selection method. This is typically small for good selection methods. So you can think of, so this KL reduction metric should be large for good selection methods. And intuitively, you can think of KL reduction as the improvement that you get in KL divergence after doing data selection. And we tested KL reduction of different data selection methods in the continued pre-training setting, where we start from a base model. In our case, it's the Roberta model, and we continue pre-training it on selected data to get this pre-trained model. And then we fine-tune this pre-trained model on target data to get the model that we actually use on the task. And we did this continued pre-training pipeline for 8 different data selection methods and averaged the results over 8 target tasks. So we did this pipeline 64 times. We made this plot over KL reduction, average KL reduction versus average downstream performance on these 8 tasks. The gray horizontal line is just the downstream performance, average downstream performance of the base Roberta model without any continued retraining. So here are the 8 data selection methods. We can see that there's a high correlation between KL reduction and the downstream accuracy with a Pearson R of 0.82. And this shows that there's the similarity in hash n-gram space is meaningful for downstream accuracy. And in particular, on the top right corner with the best KL reduction and downstream accuracy is DSER, which improves over both manual curation and heuristic filtering. With the change in the target distribution, we can actually repurpose DSER to select data for general domain language models. So let's say we choose the target to be Wikipedia and books as a proxy for high quality text. In this experiment, we'll pre-train BERT models from scratch. What we find is that the data selected by DSER produces models with 2 to 2.5% improvement on the glue benchmark over random selection and heuristic filtering, which is a significant improvement. And DSER is quite fast and scalable. We benchmarked it on selecting 100 million documents from the pile, which is about 2 billion examples. It took 4.5 hours with 96 cores on one node, and it can get faster with more parallelism. And you can do this in just 4 lines of code with the data selection package. And DSER is also used in practice at Together, Visa Research, and Salesforce AI for trillion token scale selection. And DSER importance weights are included as data quality metrics in the recent Red Pajama v2 dataset. So as a summary, importance resampling is a classic algorithm for selecting data according to a target distribution. But it depends on estimating importance weights, which are intractable to do in high dimensions. Our algorithm DSER works in a reduced feature space to make this tractable, and it results in a large-scale curation algorithm that improves over both manual curation and heuristic filtering. So the previous two sections were about two major settings in data curation for pre-training data. In the third section, I'll revisit the multipurpose pre-training setting to understand a key capability of language models on context learning, where it can quickly adapt to new tasks, with the goal of understanding the role of pre-training data on eliciting this capability. So what exactly is in-context learning? So in context learning, we have this prompt where we have a couple of examples of a task we want to do. So here we're mapping movie reviews to a numerical score from 1 to 5. We've got some training examples with the input and output, as well as a test input with only the input, which we want to make a prediction on. The model has to take this prompt and figure out what the task is. Maybe given the movie review, it should output positive, negative, or it should output this numerical score. What we find is that these pre-trained language models are able to take in this prompt, understand the task, and make the right prediction most of the time. And in-context learning is really a fundamental way to use and evaluate language models. It's enabled some of the first human-level problem-solving performance on MMOU, and it's achieved greater than 80th percentile on the bar exam, SAT, and AP tests. And in our holistic evaluation benchmark for our language models, we almost exclusively use in-context learning to evaluate language models. To contrast in-context learning with typical supervised learning, in typical supervised learning, we have a couple of independent examples of the task. And we use these examples to optimize the parameters of a model, let's say using gradient descent. And we take this optimized model, and now we can use it to make predictions on the test input. In context learning, we just concatenate together all these training examples and the test input together, feed it into the model, and makes a prediction without optimizing any parameters at all. Contrast this to the way that language models are trained, which is just to predict the next token. So it takes in some text, some context, Monty Python, and the Holy Grail is a 1975 British, and it's trained to predict the next word, which is comedy. So the mystery of in-context learning really is that language models are not explicitly trained to learn from examples. And what I mean by this is that there's a distribution mismatch between the pre-training documents and the in-context learning prompts. The prompts are typically narrower. They're about a particular task. They have a certain format, and they concatenate together independent sequences. So how does in-context learning actually arise from pre-training? I'll first step back and note that there are many angles to try to tackle this problem from. So you can understand in-context learning, for example, from the role of the model architecture or scale. You try to understand the role of the training algorithm. But we choose to focus on the role of the data on eliciting in-context learning. In particular, we will provide the first theory of in-context learning with a simplified model of the pre-training data. So to do this, we'll first posit a generative model of the in-context learning prompts. So we have some independent examples of the task. We'll first assume that they all share this latent variable, theta star, that comes from a family of latent variables, big theta. And you can think of this latent variable as capturing the input and output marginal distributions, the input-output mapping for the task, as well as the format of the prompt. And to complete this generative process, we'll concatenate these independent examples together to get a prompt. Now, if the language model's pre-training data looks exactly like this, then in-context learning isn't so surprising. The pre-training distribution is equal to the prompt distribution. And in-context learning is just standard Bayesian inference in this setting. And what I mean is, the language model can take in a prompt. It's able to understand that it should treat these as independent examples, use these examples to infer the latent variable, and then condition on that latent variable along with the test input to make the prediction. However, this isn't the case. So we posit a different generative model for the pre-training data. So here I have an example of a Wikipedia article for Monty Python and the Holy Grail. So this document has a long-range coherence structure. And what I mean is that if you take a look at the document, it's a Wikipedia article. It's got all the history and accolades and the plot all pertaining to this film. And we capture this kind of long-range coherence structure with a document-level latent variable. You can think of this latent variable as capturing the topic, the factual relations, the syntax in the document. In the theory, where we model the text as being sampled from a hidden Markov model, this latent variable is a hidden state transition matrix. And the thing to take away here is that the pre-training distribution is a different distribution of text, but it's got a shared latent structure within context learning prompts. So, and this will be important. So what we find is that if you have, let's say you have enough data in a large enough model to do the pre-training with, during the next token prediction process, the model has to learn to implicitly infer the latent variable in order to predict the next token well. And what we'll find in the theory is that it's able to transfer this capability over to prompting to be able to infer this latent variable from prompt despite the distribution mismatch, and then condition on it to make the prediction. And more generally, beyond in context learning, we find across contrastive retraining, masked language modeling, next token prediction, general self-supervised regression, that pre-training helps when adaptation tasks depend on the same latent structure as in pre-training. Okay, so in our theoretical analysis, this is the general framework of what we try to show. So we first start with an assumption. We assume that the language model is large enough in parameters, and the data is large enough such that the language model fits the pre-training distribution perfectly. So with this assumption, we remove the effect of the model architecture and the training algorithm. And given this assumption, we can write in context learning as taking the most likely prediction under the posterior predictive distribution P of y given the prompt. We can rewrite that distribution as marginalizing over a set of latent variables, where inside this marginalization, there's a weight on each latent variable, P of data given the prompt. And for in context learning to occur, ideally, this P of data given the prompt should concentrate on data star with more examples in the prompt. And so this is what we show in our analysis. So we'll under certain assumptions. So we'll assume that the pre-training distribution is a mixture of hidden Markov models where the latent variable is a hidden transition matrix coming from a family big data. And we'll also assume that the prompt conditions on some data star, which is from that same family as in pre-training. So this is an identifiable learning problem. And using these assumptions with some regularity conditions, we can show that in context learning makes the correct prediction asymptotically with more and more examples in the in context learning prompt if for all the latent variables data that's not the data star, it satisfies this inequality where the signal is greater than the noise. The signal here is measured by a KL divergence in the output distributions of the model conditioned on the prompt and either theta star or theta. And what this means is if conditioning on the prompt allows the model to distinguish better between the two latent variables, then there's a good signal in this prompt. On the other hand, the noise term comes from the distribution mismatch between pre-training and prompting. And to get a more intuitive understanding of what this is saying, it's saying that prompts provide some kind of noisy signal for Bayesian inference. Yeah, just.
Yeah, can you just go back to the previous slide? At a high level, I understand what you were saying. I was just a little surprised by you were saying mixture of HMMs, especially given the line after that. So mixture of HMMs is an HMM, and you're saying that theta is not choosing one of those HMMs, but rather is a transition matrix. So what does the mixture do?
The mixture is like you have a family of transition matrices. Mm-hmm. So when you sample a document, you first sample a transition matrix, and then you condition and that defines a HMM, and then you sample a document from that HMM.
I see, so the latent variable, when you say it's a hidden transition matrix, you mean it's one of K?
One of K transition matrices.
Okay, thanks.
That's right.
And does K have to be small in order to converge quickly?
Like in the theory?
Yeah. Presumably it shows up in the, because we formulated it this way, presumably it shows up in the convergence rate.
It's so it doesn't show up here because we're actually just having this condition hold for all the latent variables simultaneously. So when you have more, then I guess it becomes a little harder for all of the conditions to hold at the same time. But what we can show is that even when this doesn't hold, so this inequality, it goes the other way for some latent variables. This actually provides an upper bound on the KL divergence between that particular latent variable that's not data star and data star. So you can actually use that to show that the outputs are still close to what you would get under data star. So in that case, it's actually bounded by, for example, the number number of tokens in each example, which gives you more signal per example about the latent variable. Yeah, but I guess to directly answer your question, for this particular result, there isn't a dependence on the number of latent variables.
Let's check it out. Thanks.
Yeah.
Don't rush later.
Yeah.
So, if the pre-trained data contains some patterns, or like there's a distribution of these data variables, but if you prompt the model with an opposite distribution, let's say the positive reduced for given a low rating, and the negative to a high. Sometimes the language models give very pattern. In that case, the noise might be greater than the signal, but it still works. So this is good. Account for that.
I'll talk about. I'll visit that in a couple of slides. Okay, so. Okay, so just as an intuitive understanding, the examples in the prompt, the independent examples are going to give a signal for what the latent variable is. Whereas the transitions between the examples, because you've concatenated these independent examples together, they might be low probability. So this is a source of noise. And what we understand from this is that in order to do context learning, the language models have to overcome this noise to robustly infer the latent variable to enable this capability. So using this understanding, we can construct a synthetic data set that elicits in context learning. So we follow the theory exactly. We to generate from a family of transition matrices, and then sample a document from the hidden Markov model given that transition matrix. For the prompting side, we fix a transition matrix data star. We sample independent sequences from it and then concatenate it together to get a prompt. So when we train both transformers and LSTMs to popular architectures for language models on the pre-training data set, we find this in context learning behavior on the prompts, where with more examples in the prompt, the accuracy on that task improves. And in particular, because this works for both transformers and LSTMs, this suggests that in context learning is not special to transformers, which is a popular architecture used today. It suggests instead that data is a key driver of in context learning. Okay, so this goes back to your question. So there's been some empirical evidence that in context learning still works on these tasks that are unseen or unnatural. So one example is this remapped label task where we're mapping beats to sport, golf to animal, and horse to plant in a consistent way. So we remap the labels consistently, and we find that the language models with enough examples in the prompt are able to do this remap task that it may not have seen before. And with respect to our Bayesian inference framework, language models should only be able to infer latent variables that are seen during pre-training. So how can this occur? So some recent follow-up works have extended our framework to compositional latent variables to enable this kind of extrapolation. So for this particular example, you can break it down into two component tasks. You first classify, and then you do this remapping, which is a kind of copying task that is seen a lot during pre-training. And so these are components that are learned during pre-training. As long as the model is able to put them together compositionally, which is something that certainly we don't understand yet, then this kind of extrapolation can occur. Some other applications of our context learning framework include furthering the empirical understanding of context learning. So, for example, explaining the robustness of context learning to randomly shuffling the labels, which would break traditional supervised learning. And inspiring new algorithms for context learning, including choosing better examples in the prompt to improve the latent inference, and also tuning the model itself to change its latent representations to improve the signal-to-noise ratio. So as a summary, language models are not pre-trained explicitly to do in context learning because there's a distribution mismatch between pre-training and prompting. However, if the pre-training and prompting distributions share the same latent coherence structure, then during pre-training, language models will naturally learn to infer this latent variable. And what we find is that they're able to transfer this capability to infer the latent variable robustly, despite the distribution mismatch to enable in context learning. Now, I'll wrap up the three sections by just noting that in each section, we touched upon a connection between pre-training and robustness. So what I mean is that, for example, in optimizing data mixtures, we use distributionally robust optimization. In selecting data for a specific target, we used importance weighting, which is a technique that's classic in domain adaptation. And finally, overcoming the distribution mismatch between pre-training and prompting was core in enabling in context learning. It's clear that there's a deep connection between pre-training and robust machine learning. And this shouldn't be too surprising because within the setup, there's an inherent distribution mismatch between pre-training and adaptation. And I'll say a little bit more. So in the first two sections, we use robustness techniques to improve the generalization from pre-training to adaptation by reducing the distribution mismatch, which is mostly an input or handcrafted feature space. And in the last section, our theory of context learning motivates new algorithms which work in latent space. Okay, so I'll look a little bit further into the future. And I'll say that I envision models that efficiently and continually learn and scale with less dependence on human-generated data. So if you revisit the modern machine learning pipeline, there's a heavy reliance on human-generated data. I envision a new data-centric machine learning cycle, which starts with the same steps, but extends it to do large-scale and adaptive evaluation and also data generation with the model with the help of interaction with an environment, humans and other models for a source of external supervision, to be able to close this loop and create a cycle of self-improvement with less reliance on human-generated data. My future directions in continual learning and scaling, generating training data, and generating evaluation data work towards this vision. So in the first direction, I'll first introduce this plot between model size and data size. Plotted a couple of open weights models here. On this plot, you can visualize the compute cost for training Llama, for example, as a product between the two axes. And if you want to develop Llama 2 starting from Llama, you have to, right now you have to pay all of that compute cost and then some. But we really shouldn't have to start from scratch. We should be able to incrementally improve and scale both the data size and the model size. So as an example challenge in continually scaling data, how do we update the model efficiently without forgetting? To mitigate forgetting, often you'll try to mix in some old data, And you can think of this as some kind of data reweighting problem. You might be able to use a data curation algorithm that we talked about to balance the old and new data. But now there's a trade-off. There's a trade-off with the efficiency of learning on new data, since you have to mix in old data in order to learn new things. So can we avoid this, or is this a fundamental problem? An example challenge in continually scaling models is in how do we leverage smaller pre-trained models with a different architecture? The fundamental challenge here is that you have these smaller pre-trained weights that don't type check with the bigger model that you're trying to train. And one idea here is that data is a shared interface between these models. All these language models or generative models are models of the data distribution. So this motivates using tools like distillation or data generation to supervise the larger model from the smaller. And this brings me to my second direction in generating training data. And I'll introduce this first by talking about the levels of human supervision over time in machine learning. So in the past, we depended a lot on supervised learning, where humans generate both the inputs and the outputs for the model. In the present, there's all of these pre-trained language models use self-supervised learning, which depends on large-scale human-generated inputs, and they kind of supervise themselves by predicting the next token. Perhaps in the future, we'll have a more self-directed learning paradigm where models generate the inputs that they want to train on, and with the help of some interaction, we can generate better outputs to supervise themselves on as well. So to go into this a little bit further, so an example challenge in generating training inputs is in generating diverse data that's also relevant. And a promising framework, example framework here is in using the DRO for this task. So in DRO, we need to define a set of distributions over which to maximize over. And this is a natural way to think about a relevant set of data. So let's say we use a language model to define this relevant set of distributions. We'll only generate reasonably likely data under a language model. So this gives us a definition of a set of distributions to maximize over. And then the second component of DRO is that we're maximizing this loss. So in DRO, we'll generate data that maximizes the loss with respect to a currently training model. And then if you think about this in a continually learning loop, we'll use this data to update that model. Now, a different part of the data set will maximize excess loss. And if you continually generate this data set over time, you'll get a naturally diverse data set. And there's some connections here to controllable and diverse generation, perhaps even creativity and generative models. On the training output side, an example challenge is to generate data with a language model P old, such as GPT-4, let's say, to train a more capable model P new, such as GPT-5. And this might sound very degenerate as a setting, but it's important to have some kind of leverage. So the leverage, one example is to obtain extra information about latent variables to help make a better prediction. So as an example, let's say we have an input scientific question X that GPT-4 doesn't know how to answer. Let's say we expend some effort to collect some extra information about latent variables. This might be the relevant papers for answering this scientific question. This might be new experimental data that we need to collect to answer the question. In general, this step might be compute intensive. It requires some interaction with an environment. And but let's say we're able to estimate these latent variables somehow. We can then condition on both X and Z to generate the better prediction using the old language model. And now that we have the latent variables and the predicted output, we can use these as supervision for the new model. And then finally, my third direction is in generating evaluation data. I'll introduce this by saying that language model evaluation is just a very difficult problem, and it's similarly difficult to human evaluation. There are many challenges, including including that we want to test qualitative criteria like fluency, bias, and helpfulness. And these models are changing so fast that these evaluations are quickly becoming deprecated. To draw an inspiration from human evaluation, we typically have human experts like professors create evaluations like exams to test other humans like students. So I'd like to draw the analogy and generate evaluation data with models. An example challenge here is to specify and test the qualitative criteria such as bias or helpfulness. And one promising approach could be to use the efficient adaptation abilities of pre-trained language models that already have some idea of these qualitative criteria to specify these criteria with minimal, hopefully minimal human input. To put on our data distributional hats, we can think of, for example, the distribution of Q&A questions that are relevant for testing helpfulness as some kind of target distribution. And with some amount of human input, we can use a language model, pre-trained language model, to model this target distribution. And now we have a way of defining the relevant set of distributions to use within a data generation algorithm that we talked about before. However, the twist to this is that the target distributions will naturally shift over time. So, for example, the relevant questions that people ask will naturally shift over time, and the way that we interact with models will change as the models are changing as well. So, an open question here is how can we build adaptive and robust evaluations by leveraging the latest models and data? So to conclude, data is key for capabilities in language models like in context learning. However, current data sets are built in an ad hoc and heuristic way, and so there's a large room for innovations and improvements here. Now, I've talked about two principal algorithms for curating better pre-training data by manipulating the data distribution called Doremi and DSER today, but there's a lot more work to be done in this space. Thank you, and thank you to all my collaborators and my funding sources.
Great, well, we have a little time for questions, especially from people who haven't asked anything yet.
Yes.
This one, I guess, running with this like variable interpretation.
Mm-hmm.
I really want these models to kind of explore the world themselves and make connections we haven't thought of before. Like maybe we should be thinking kind of like hierarchical agent managers, right, to allow them to have like ability to reason across different contexts or something like that. Is this direction thought about or makes sense? Or?
So could you clarify a little bit? So this is above the level of a document, I guess.
Exactly. Yeah. And if you think of it, I interpreted how you were just saying your model is I would think of a context as like a document that has a latent variable to it. Mm-hmm. Now we need to kind of start connecting latent variables in different contexts or something like that. That's how to think about it.
That's an interesting idea. I think there's been some work recently that's shown that if you put together documents that are more similar in the same context window when you pre-train, this helps the model with long range, long context abilities, and in turn helps it pay attention to all the examples in the in-context learning prompt. So I think, yeah, there could be some higher level latent structure to leverage here in even just the ordering of the pre-training data. Yes.
Start with the first thing where you had a reference model and you were using the domain weights. So when you're using excess risk with these reference weights, which are like on the natural training distribution, how do you avoid the first iteration itself overfitting on the same distribution? Because you're just optimizing for the excess risk, and maybe the reference model achieves a high risk on a less seen domain, and the access risk is not there. So how does the new model amplify that?
Yeah, so I think the intuition is that you'll be able to tell when adding more examples is not improving the loss very quickly. And as a function of this, you'll close the gap to the reference model as quickly as possible. And so if you're able to reduce the number of steps needed to get to the reference model, then you'll have some additional budget to improve beyond the reference model. And then once you do that, you can think about looping that back in as the new reference model. So if you think about this process as a whole, there's maybe a chance to escape from some of the pitfalls you're talking about.
This is like an empirical phenomenon.
That's true, yes, because we don't have a theoretical analysis of the fixed point of this process.
So when you talk about like the ICL, inputting latent the latent variables,
Yeah.
while doing this, do you think that only applies to tasks like let's say mathematics or like direct tasks, or you can have latent variables that model can infer about tasks like trustworthiness, helpfulness, or some of these broader topics?
That's a good question. So I guess the true latent variable is sort of unknown. Like we have a theoretical construction in our generative model of what that is. That's the transition matrix. So certainly it could be anything, I guess. But I guess whether it's useful is another question. I think it's probably, yeah, it's plausible that like when in the generative model of like when we're writing a particular response, we first decide to be helpful and then generate that response. So it's possible that aspects of those qualitative things that we want to test are also in there. Yep.
I'll ask one question just because we have a little bit. So this is really going more back to the first part of your talk, Dorothy. It's a little jarring to think about domains. So you just have, like a strict partition of documents, whereas the language models themselves have these really deep representations of the documents.
Yes.
So there's intermediate things also, like, you can imagine every document has a bunch of features.
Yes.
In a sense, what you're doing is just learning hyperparameters of some model that tells you how much to weight a given document. And if you just say every document has exactly one feature, namely the domain it's from,
Yes.
you're probably leaving something on the table. Can you say anything about that?
Yes, definitely. So certainly, reweighting the data set on the level of domains is very coarse. And there's definitely opportunities here to make this more fine-grained. An obvious way to go about this is to, let's say, use the embeddings of some language model, cluster the data, and you have more partition the data according to those clusters. I think in general, you want to think about this as you're actually trying to learn a function from a weighting function from input features to the weight. And because what you get to in the extreme cases, let's say one domain is just one example, now you're in a situation where if you put a scalar value for every domain, then you're not going to be able to decide what weight to put on that example until you see it. So you need to be able to share information across domains somehow. Embeddings is one way, parameterizing this function is another way. So there are some technical challenges there as well to because right now, for example, the algorithm depends on gathering some information about every domain in every step before we update the domain weights. And with more domains, you'll have to either wait for longer to collect more data before updating, or leveraging some structure to share information across domains. So there's some work to be done there, but certainly there's a lot more flexibility and power that you can get from a more fine-grained approach.
Thanks. Okay, well, let's thank Michael again. I should have said when I introduced him that he plays the piano and he also plays the basketball.
Thank you.